Welcome back to Introduction to Oceanography. This is Chapter 9 from Essentials of Oceanography, the 7th edition by Tom Garrison. And in this chapter, we will be taking a look at waves. Waves transmit energy, not water. That's important. Waves do not move water across the ocean. They move energy across the ocean. Ocean waves are orbital. They're almost like circles in which water molecules move in those closed orbits as the wave moves by. Ocean waves are classified by the disturbing force that creates them, the extent to which the disturbing force continues to influence them once they're formed, and by their wavelength. The speed of an ocean wave is proportional to its wavelength, something that's going to be a mathematical part of this chapter, and it's going to be very interesting to see how wavelength and speed change with ocean waves. And most characteristics of ocean waves depend on the relationship between their wavelength and the depth of the water in which they're traveling. The orbits of water molecules and waves moving through water deeper than half the wavelength are unaffected by the bottom. That means in deep water, waves can be unaffected by the bottom. The wavelength of a tsunami and tides are so great that they're always affected by the bottom. So they're always considered to be in shallow water. And water displacement causes tsunamis and seismic sea waves. That's going to be very important when we talk about earthquakes and what creates tsunamis. Tsunamis literally not noticeable in the ocean, but they rush ashore like a sudden and very high onrushing tide. They are huge, shallow water waves and are among the most lethal of our planet's natural phenomena. All right, ocean waves move energy. Ocean waves do not move water. They move energy. Ocean waves are visual proof of the transmission of energy across the surface of the ocean. To the right, we can see a floating seagull, and it demonstrates the way a wave travels, but the water does not. You can see the wave moves from left to right, and the gull, and the water in which it's resting, revolve literally in a circle, moving slightly to the left, up the front of the approaching wave, then to the crest, and then sliding to the right down the back of the wave. And we can see how that works in this illustration below. There's no mass transport there's no mass transport. Nothing moves. Water doesn't move. The energy moves through the water. And so in the actual wave, there is this very small amount of movement, which is known as Stokes drift. And that is the amount of transport that actually happens in an actual ocean wave. So in reality, there's a small net movement forward, and that's known as Stokes drift. And this contributes to the motion of wind-driven surface currents. The height then is between the top of the crest and the base of the trough. That's going to be the height. Now the frequency is the number of wave crests, crest 1, crest 2, passing point A or B each second. So for every crest that passes by per second, that's the frequency. The period is the time required for a wave crest at point A here to reach point B. And again, this is the orbital path of the individual water molecule underwater. So orbital waves are waves in which the particles of water move in closed circles as the water passes. Note that the water molecules in the crest of the wave move in the same direction as the wave, but molecules in the trough move in the opposite direction. But they also move more slowly, and the fact that they move more slowly is why you have that orbital drift or that Stokes drift. How do we classify waves? Scientists always want to classify natural phenomena, so we're going to classify waves. We have the wave type, the disturbing force, the restoring force, and then the typical wavelength. So we're going to classify the wave type as capillary waves, wind waves, a seiche, a seismic sea wave, or a tsunami, or a tide. And the disturbing force of a capillary wave is wind. Disturbing force also of a wind wave is wind. A seiche is a change in atmospheric pressure, or which could also be storm surge. A seismic sea wave is faulting of the seafloor, a volcanic eruption, or a landslide. And the disturbing force of all tides is the gravitational attraction of the Earth, Sun, and Moon, and the rotation of the Earth. Now, what causes waves to, so that's what disturbs waves, these issues. What causes waves to go back to where they were? Capillary waves, little tiny waves, the cohesion of water molecules can actually bring them back down to flat. And all other waves, it's the restoring force is gravity. Now, the typical wavelength of capillary waves is just very, very small, just over ½ of an inch. The typical wavelength of a wind wave is anywhere between 200 and 500 feet, And then a sea is going to be much larger and variable as a function of the ocean basin. A seismic sea wave can have a wavelength. That means the distance between crests of a tsunami could be as much as 125 miles. And then the wavelength of a tide is half the Earth's circumference. So, ocean waves are classified by the disturbing force that creates them, the extent to which the disturbing force continues to influence the wave once it's formed, and the restoring force that tries to flatten them. So the disturbing force creates the wave and continues to influence the wave, and the restoring force is the force that tries to flatten them. And the third way that they're going to be classified is by wavelength. Free waves propagate across the ocean without further influence of the disturbing force. So a free wave is going to be disturbed by wind and then continue to move across the ocean. And most wind waves are free waves. Forced waves are maintained by the disturbing force. So tides are considered to be forced waves. And a restoring force is the dominant force that returns the surface to flatness after the wave is formed. Waves continue after they form because the restoring force overcompensates and creates an oscillation. So a wave, once it leaves its disturbing force, continues because the restoring force tends to create overcompensation, meaning it may pull the wave down to the surface level, but it also pulls it below the surface level, and so it responds by going up above the surface level. So waves that continue after they form, free waves, do so because the restoring force overcompensates and creates an oscillation. All right, so this is how your typical wind wave, and so this is going to be a capillary wave, very, very small. Wind waves are formed by the transfer of wind energy into the water. Wind waves grow from capillary waves. So all wind waves start as capillary wave. Capillary wave forms as wind friction. Literally, the friction between the wind and the surface of the water stretches the water, and the surface tension tries to restore the water to smoothness. So the wind stretches the water out, and surface tension tries to pull it back. The capillary wave interrupts the smooth sea surface, deflecting surface wind upward, slowing it, and causing some of the wind's energy to be transferred into the water to drive the capillary wave crest forward. Essentially, the wave blows across flat water, stretches it, pulls it up, and creates this very tiny capillary wave. The increasing energy in the water surface expands the orbits of water particles moving in the direction of the wind and enlarges the wave size. So once the capillary wave is formed, this tiny wave, continued wind blowing into the back of the capillary wave expands the orbits of the water particles moving in the direction of the wind and enlarges the wave size. So this is what it looks like with capillary waves, with the wind stretching the water, the surface cohesion of the wave, of the water that is, trying to pull it back to flatness, and you're getting the capillary waves. Continued wind blowing in the back of the capillary waves causes those waves to continue, and eventually the restoring force of gravity pulls the water down below the surface, and then it comes back up, and you get the free wave that continues. So capillary waves become gravity waves as their wavelength exceeds 1.74 centimeters. So once it gets above 1.74 centimeters, then you have these gravity waves, these free waves. Wind-induced gravity waves, or wind waves, continue to grow as long as the wind above them exceeds their speed. So if the wind is blowing faster than the speed of the wave will continue to get bigger. Now, wind waves will exhibit a maximum 1:7 ratio of wave height to wave length. So this is the wave height from the trough to the crest. This is the wavelength from one trough to the other. Wind waves exhibit a maximum 1:7 ratio. The angle of the crest will not exceed this 120-degree angle. A peaked appearance indicates a continuous injection of wind energy. If a wave becomes higher than the 1:7 ratio, it will break, and that's where you get white caps. So winds will look like these peaks in the water until you get to this greater than 1:7 ratio, and then you'll start to get white caps, and that occurs in what is known as fully developed seas. So, wind speed, the wind must be moving faster than the wave crest for energy transfer to continue. So these are the wave or the wind wave development factors. The wind speed must be moving faster than the wave for the energy transfer to continue. Wind duration, winds that blow for a short time will not generate large waves. Winds that blow for a long time, however, will generate large waves. Fetch is the uninterrupted distance over which the wind blows without changing direction. So if the wind is blowing a straight line over a great distance, that's a long fetch of wind, and that's more likely to develop larger waves. And so this concept of a fully developed sea is the maximum wave height theoretically possible for a wind at a specific strength, duration, and fetch. A strong wind must blow continuously in one direction for nearly 3 days for fully developed seas to occur. Longer exposure will not increase the wave height as the wave energy is lost to the breaking wave top. So this idea of fully developed seas, the biggest wind wave you can have from a type of wind is a function, again, of the wind blowing across a specific stretch of ocean for a specific period of time. And a fully developed sea typically takes 3 days to form. So the fetch of the uninterrupted distance over which the wind blows without significant change in direction. The fetch is that uninterrupted distance. This is the fetch of the wave, from where the wind's blowing all the way to where it's no longer blowing. Wave size increases with increased wind speed. Faster the wind, the larger the wave. Increased duration of wind, the longer it blows. And the fetch, the length of distance, that is, that the wind blows over. A strong wind must blow continuously in one direction for nearly 3 days for the largest wind waves to develop into the fully developed seas. All right, larger swell move faster. So this is going to be an interesting look at wave trains and how waves move through the open ocean. Wave separation or dispersion is a function of wavelength. Waves with the longest wavelength move the fastest and leave the area of wave formation sooner. So longer wavelength waves will move away from the area of the disturbing force more quickly. The smooth undulation of ocean water caused by wave dispersion is called swell. So here at the left, waves travel in groups called wave trains. So 1 through 5, 1 through 6, 1 through 7, those are wave trains, okay? As the leading wave of the group travels forward, it transferred half of its energy forward to initiate motion in the undisturbed surface ahead. So as the leading wave moves along, it transfers energy forward and causes a wave ahead of it. The leading wave in the wave train continuously disappears while a new wave is continuously formed at the back of the train. In this case, we have 5, and then 6 is formed, and then 7 is formed, and then 8 is formed. The wave train travels at about half the speed of any individual wave. And so that speed of the wave train is known as group velocity. So how do waves behave in different water depth? Again, if you take the wavelength L and divide it by 2, that is the depth in which wave motion or orbital motion stops. So there's no perceptible motion underneath this depth. So as the wave moves into shallower and shallower water, you begin to lose that depth, and it starts to impact the behavior of the wave. So ocean waves and how they act depends on the relationship between the wavelength and the water depth. Wavelength determines the size of the orbits, but water depth determines the shape. So how big these orbits are a function of the wavelength, with the longer wavelength having much larger orbits. They are nearly circular in open water, but once they get into a depth that's half their wavelength, those orbits begin to flatten out. So a wave cannot feel the bottom, meaning these waves are not feeling the bottom until the water is half the wavelength. So out here in the deeper water, they don't feel the bottom. Once they get into the shallower water, they begin to feel the bottom. When the water depth is half the wavelength, the orbits are flattened out and they become transitional waves. When the water is less than 1/20th of the wavelength, it's considered a shallow water wave, and that's typically where you start to see these breaking waves. In general, the longer the wavelength, the faster the wave energy moves through the water. As water depth decreases, a wave can begin to feel the bottom, and then the wave speed slows. And what ends up happening is, because the wave speed slows, as these waves here feel the bottom, the wavelength between the wave also shortens as the wave approaches shore. So deep water waves speed is proportional to the wavelength, and shallow water wave speed is proportional to the depth. Again, the speed of these deep water waves has to do with the wavelength. The speed of these shallow water waves has to do with the water depth. Wave period does not change as water depth changes, so wavelengths shorten. Waves bunch up as the depth increases. So deep water waves change into shallow water waves. These are the events that lead the wave to break. First, the wave feels the bottom when the water depth is less than 1/2 the wavelength. Second, the circular motion of the water molecules in the wave is then interrupted. Wavelength decreases, but the period remains the same. That was the last point of the previous slide. The period, the number of wave crests that pass a point, remains the same, but the wavelength decreases. Waves become too high for the wavelength, meaning the top of the wave becomes too high, and the crest will move ahead of its supporting base, causing the wave to break. So here that is graphically illustrated. The swell feels the bottom when the water is shallower than half the wavelength. So here it's half the wavelength, and the wave begins to feel the bottom. The wave crest becomes peaked because the wave's energy is packed into less water depth. So it pushes it up and it becomes peaked. These orbitals become more elliptical. Constraint of circular wave motion by interaction with the ocean floor slows the wave. It slows down while the wave behind it maintains the original speed. Therefore, the wavelength has to shorten. The distance between the waves becomes shorter. That's like when you're standing in the surf zone, the waves are closer together than they are out in the open ocean. The period remains unchanged. The number of waves that will pass a certain point at a time remains the same, but the distance between them shortens up. At 4, the wave approaches the critical 1:7 ratio of wave height to wave length. When it passes that ratio, the top of the wave literally continues moving faster than the bottom of the wave. So at 5, the wave breaks when the ratio of wave height to water depth is about 3 to 4. The movement of the water particles is shown in red here. Note the change from a deep water wave through the transitional wave stage to a shallow water. So here it's a circle, here it's an elliptical, and here the water is literally moving back and forth after that water breaks. And this is after that wave breaks, and this is known as the surf zone. So 2 different types of waves. Waves that we typically see here in Florida are spilling waves. They just sort of crumble over one another. And then we have plunging waves, the waves that sort of pitch out and create, the tube as surfers call it, or sort of pitch out and are more hollow. So plunging waves will break violently against the shore, leaving an air-filled tube, the tube that surfers talk about, or a channel between the crest and the foot of the wave. Plunging waves are formed when waves approach a shore over a steeply sloped bottom. So essentially, the plunging wave is this. So if this is, let's see if I can draw this for you. If this is the bottom, as the wave comes in like this, if it's steeply sloped, the top of the wave gets thrown out while the bottom of the wave literally stops, and you get that plunging wave. Not the greatest picture in the world, but you get that plunging wave. That's the tube. Okay. If you have a shallow slope, it's a more gradual slope. It's a more gradual slope like this, then those waves will tend to crest and they'll just sort of crumble down. And that's kind of what we see here in Florida, where the wave, it doesn't plunge, it just sort of spills over and crumbles down. So spilling waves occur on gradually sloping ocean bottoms. The crest of a spilling wave slides down the face of the wave as it breaks on shore. All right, where would you typically find the biggest waves? You'd find them where you had the highest winds. And you have the highest winds where you have the mid-latitude westerlies moving across the Pacific and the Atlantic Ocean, and then very specifically the westerlies moving across the southern Pacific, the southern Indian Ocean, and even to a lesser degree the southern Atlantic Ocean, because these southern oceans, the winds are not impeded by land. There's a lot of open ocean. The wind's only slightly impeded by land here, not impeded by land, and so your highest winds are across this section of the Southern Ocean, and it's that section of the Southern Ocean where you do see those wave heights up to 5 to 6 meters. So In this image, the highest waves occur in the Southern Ocean, where the waves are more than 6 meters, 20 feet or so high. The lowest waves are found in the tropics. Remember, the tropics are where we have the doldrums. These are the where not much happens. There's not a whole lot of wind, and therefore there's not a whole lot of waves. What happens when waves from different storm systems exist simultaneously? So if you think about the open ocean, you might have wind coming from the northern Atlantic Ocean, maybe some wind coming from a tropical system down closer to the Caribbean. And all these different winds will likely generate different types of wind waves. So what happens when different waves from different storm systems interact? Well, when they meet, they interfere with one another. And there's two types of interference, destructive and constructive. And so destructive interference is when two waves that actually cancel each other out, resulting in a reduced or no wave at all. So two waves can come at each other from two different directions and really serve to cancel themselves out. More often, we see constructive interference, where there's additive interferences, where the waves actually add to each other, and that results in waves that are larger than the original waves. But it's going to be a combination of both, depending on how and what angles the winds and the waves meet at. And so what you get is this offset of lots of different size waves moving through the same region, and that cycle of larger and smaller waves that we hear in the breaking surf is what's known as the surf beat. So surf beat's not just a type of music, but it's actually a scientific term referring to the cycle of a set of larger breaking waves followed by a lull in the surf and then smaller breaking waves. Now, if you have lots of constructive interference, you can get these freak waves that occur that become gigantic, and those are rogue waves. And that is when you get a wave that the crest is higher than the theoretical maximum of those waves. And you mainly see that again down in the Southern Ocean. So constructive interference and destructive interference. Two overlapping waves of different wavelengths are shown, one in blue and one in green. If both are presented in the ocean at the same time, they'll interfere with each other to form a composite wave. So the composite wave is actually the one that's going to be in green here, the two different waves in red. So the different waves have essentially different wavelengths. So there are periods of time when they're synced together and they have constructive waves, and periods of time when they're synced apart and you create destructive interference. And so you get additive situations here and then destructive situations here. At the position of line 1, the two waves will constructively interfere with each other to form large crests and troughs. And then at B, at the position of line 2, the two waves will destructively interfere and the crests and troughs will be much smaller. So that's the result of both constructive and destructive interference. So here's a sea level trace at this oil platform in the North Sea back in 1995, where constructive interference was responsible for a wave of almost 19 meters. So we're talking 55 to 60 feet. And you can see you had pretty typical surf beat with some constructive interference and then destructive interference, somewhere in between. And then some constructive interference created this tremendous peak of this wave, and that's one of those rogue waves. Three things that happen to waves, particularly as they approach the shore: refraction, diffraction, and reflection. Wave refraction, the slowing and bending of waves in shallow water. Wave refraction occurs because waves usually approach shore at an angle. The part of the waveline closest to the shore slows down as it can feel the bottom. The part of the wave further out moves faster, so it catches up to and passes the part of the waveline in the shallower water, and that causes the wave to bend or to refract. Diffraction is when a wave literally propagates around an obstacle, essentially for the same reason. A straight wave hits an obstacle. At the center of the wave, where it hits the obstacle, the water is shallower, and it causes the wave to literally bend around that obstacle, and that is diffraction. And you also see reflection, when a wave bounces back from an obstacle that it encounters. Reflected waves can cause interference with oncoming waves and create standing waves. Think about the last time you were at the ocean, when the wave rolled up the seashore, then rolled back down. Sometimes it creates a little standing wave in just an inch or two of water. That is interference creating that standing wave. So this is what that looks like. The wave progression is coming in at this angle. So this is the shoreline down here, and this is the angle. You got a nice, let's say this is a shore facing east, a nice north wind blowing a northeast wind swell in. This wave propagates along at the same speed. Again, once the wave begins to feel the bottom, where the depth is half the wavelength, then the wavelength begins to shorten and the wave starts to slow down. But these waves are moving at the same speed, and it literally causes these waves to bend and also causes them to essentially come in almost straight parallel to the coastline. So that's what we typically see at the beach is waves coming straight in, because as they felt the bottom, they will begin to bend and straighten out. And so where you get waves coming in at a sharp angle to the beach is where the water depth is deep and then becomes shallow very abruptly. Here in the Atlantic Ocean on the east coast of Florida, the ocean bottom gradually slopes out, and so you have this enough time for these waves to literally refract and then come in straight to shore. But this is refraction. Here the water's deeper, here it's shallower. Where it's shallower, the wave moves slowly and the wavelength decreases. Here the wavelength is the same and the wave is moving more quickly, and it causes the wave to bend, to refract as it approaches shore. And you can see that refraction as it comes along the shoreline. Here the waves are coming in. This is the angle they're moving, and as they come along the shoreline, they refract and bend into the shoreline, where in most cases they're almost coming in parallel to the shore in every location. So wave refraction again, waves coming in at this angle here, and they refract and bend in, so they're coming almost straight into the ocean. And here's the diffraction. When the waves are coming in straight here, as they hit this little island and get shallower, the waves begin to slow down, and so they bend around just like they were if it was just a straight coastline. And then over here, you get this constructive and destructive interference. So wave diffraction past an island chain. Polynesian navigators use diffraction patterns to sense the presence of islands out of sight from the horizon. So if you were a canoe coming along this way and you didn't see this island, you would get this constructive interference, and you know that somewhere off in the distance there was an island. So that is going to be your diffraction and your refraction. And then again, you also have the reflection. So storm surge is an abrupt bulge of water. So it's kind of like a wave, but it's a bulge of water driven onshore by a tropical cyclone, hurricane, or frontal storm. So it's created by sustained onshore winds. The storm motion and the wind motion is in this direction, coming from offshore to onshore. And it literally pushes up a mound of water. Now, there was a time when we thought that the low pressure of the hurricane may have lifted up that mound, but we now know that pressure-driven storm surge is only about 5% of the total. All the rest of it is wind blowing that water and causing it to pile up. Strong onshore winds have a component in storm surge as they cause winds to pile up ahead of the driving wind. They can be very short-lived, but they can be up to, so 7.5 meters, we're talking 20 to 25 feet. It can raise the level of the ocean. So this mound is almost like a tide coming in and raising the level of the ocean, because the breaking waves caused by this wind literally break on top of the storm surge. So storm surge consists of only a crust, so they really can't be assigned a wavelength or a period, not really called a wave either, but it definitely brings the water up and causes serious damage. As a matter of fact, most of the damage from hurricanes and deaths from hurricanes is caused by the storm surge. Standing waves, water rocking back and forth at a specific frequency in a confined area is called a seiche, and it's also known as a standing wave. Now, you can get standing waves in rivers where the water is moving along, and for some reason it gets diffracted off of an obstacle, and not diffracted, but reflected off of an obstacle and moves back down. You can also get a standing wave in the situation where you have the ocean wave moving up the seashore. So try and draw a couple of these for you. If this is your seashore and your wave is moving up it, and it gets to a point where it stops and then moves back down, this motion back down can create a standing wave right here, where there's water motion in and there's water motion out, and you get the standing wave. You can also get that in a river situation where the river is flowing along like this, but some obstacle, maybe there's a boulder here, causes water to bounce back off, and again, you'll get that standing wave in one spot. So that's what standing waves are, but we also have these standing waves that happen in enclosed basins. So maybe this is a lake or a tidal basin, but it's going to be an enclosed basin, and water is going to oscillate back and forth in this closed basin, and essentially is a standing wave where the water goes up and down and up and down. So water rocking back and forth at a specific frequency in a confined area is called a seiche. A seiche is also known as a standing wave, a wave that oscillates vertically with no forward movement. Just like the waves I just drew for you, they go up and down, but they have no forward movement. The node is the position of a standing wave where water actually moves sideways but does not rise or fall. So this is a standing wave going through its whole sequence from 1 to 5 and then back to 2 again. So it just is up and down motion, but no back and forth motion. So water can rock back and forth in a confined basin, and this happens sometimes in the Great Lakes, where at one side of the Great Lake you have high water, and at the other side of the Great Lake you have very low water. And so that's an example of that standing wave. The Great Lake represents the standing basin, but wind blowing over that Great Lake for a long period of time can create a wave where water pushes to one side and then essentially sloshes back to the other side. Tsunamis and seismic sea waves. Tsunamis are very, very long wavelength, shallow water, shallow because their wavelength is so long, they're essentially always in shallow water, even in the deep ocean. They're progressive waves caused by the rapid displacement of ocean water. Tsunamis are essentially created by the vertical movement of Earth along faults. They're called seismic sea waves. So this is your ocean basin, that's the surface. This is the sea bottom, and there's a fault along that sea bottom right here. And the pressure of that fault is pushing this part of the rock up and this part of the rock down. Maybe it's a convergent fault boundary. So over many thousands of years, just pressure builds up, and then suddenly one day, this fault gets forced up, and the sea bottom actually gets pushed up. So it looks something like this. Well, it displaces all of this water, and all that water gets pushed up, and that displacement of water causes your tsunami, your initial tsunami to form, and then propagate away. Now, they will also back up a smaller wave, but the major tsunami is going to move in that direction. So a seismic sea wave or a tsunami is generated by the vertical movement of Earth along faults, and they are seismic sea waves. Tsunamis are always shallow water waves because they're extremely long wavelengths. You can also get a tsunami generated by a landslide, so a lot of earth coming down the side of a mountain into the ocean. Icebergs calving, when icebergs are part of the ice sheet and they fall off into the water. It's called calving. So icebergs falling from glaciers, volcanic eruptions, asteroid impacts, any direct displacement of water will cause a tsunami. And they are devastating, much like storm surge. They create most of the deaths that you would attribute to ocean waves. Most recently, we had the Indian Ocean tsunami from an earthquake back in December of 2004. And it was exactly the situation I showed you. We had a convergent plate boundary where this plate was moving up into this plate, and once it was forced under it, here's the fault, it pushed this land up, and it created that ocean wave. Now, the main wave moved away, but also the tsunami moved toward land. So it happened just offshore Jakarta, and so this wave washed up in Jakarta, creating a tsunami there. So the Great Indian Ocean Tsunami, 26 December 2004, began when a rupture along a plate junction lifted the sea surface about 10 meters. Gravity, so the first thing that happens is the sea, it gets lifted up. So that's the disturbing force. What's the restoring force? Gravity is the restoring force. So it pulls it back down, but it doesn't necessarily pull it just back down to sea level. Gravity pulled it further down than sea level, and so that it needed to be restored back up, and it went up beyond sea level, and then back down, then back up, and then back down. And so that's how this displacement of water creates a wave. Gravity pulled the crest down, overshooting sea level and creating a trough. The oscillating ocean forced a progressive wave that radiated from the epicenter in all directions. The wave moved outward at, this is astonishing, 472 miles per hour. That's how quickly it moved across the ocean because of the tremendously long wavelength. At this speed, it took about 15 minutes to reach Sumatra and about 28 minutes to get across the Indian Ocean. And so this is a very classic scenario of a tsunami. Same thing happened in Haiti with an offshore earthquake causing the displacement of the ocean, and a tsunami radiated away from that area. All right, because tsunamis have extremely long wavelengths, they're always in shallow waters, they always behave as shallow water waves. The tsunami is always in contact with the ocean floor, and sometimes it's actually guided and refracted by the seafloor topography. So the speed of a tsunami can be calculated using the same formula as for other shallow water waves, which that speed is the square root of gravity times the depth. So C equals the square root of gravity times the depth, the average speed of about 470 miles per hour. So your gravity is 9.8 meters per second squared, and the depth of the Pacific abyssal area is about 4,600 meters. So you multiply those two things together and take the square root, and you get that average speed of a tsunami of 212 meters per second, or 470 miles per hour. So here is the wave height again from the tsunami that happened, well, the earthquake that happened just off Japan with the disaster with the nuclear power plant, and the tsunami that radiated away from it because of that earthquake. So that's Japan, the Aleutian Islands, and the west coast of the United States. And that's what it looked like in terms of travel times, how long it took that ocean wave, that shallow water wave, that tsunami wave, to reach even as far south and east as the south coast of South America. It took just under a day. So that wraps up Chapter 9. Waves transmit energy, not water. So waves move energy across the ocean. Water does not move across the ocean surface. And the speed of ocean waves usually depends on their wavelength. And we showed you that formula back here, where the speed of the ocean wave is really a function of the depth of the ocean. The deeper the ocean, the faster the ocean wave. So because it's the square root of gravity, which is a fixed thing, 9.8 meters per second square, 0.8 meters per second, times the depth. And so as the depth gets lower and lower and lower, shallower and shallower, the speed of the wave is going to get slower and slower. All right. The speed of ocean waves usually depends on their wavelength, with long waves moving fastest. Long waves moving fastest, and waves moving in deeper water moving fastest. Arranged from short to long wavelengths, and therefore from slowest to fastest, ocean waves are generated by small disturbances, capillary waves, by wind. Wind also moves wind waves. The rocking of water in an enclosed space creates seishes. Seismic and volcanic activity or other sudden displacement of water creates tsunamis. And then the wave that we're going to talk about next, tides. So the behavior, and of course the disturbing force for tides is going to be the gravitational attraction between the sun, the moon, and the earth. The behavior of waves depends largely on the relation between a wave's size and the depth of the water which it's moving through. Waves can be refracted or reflected. They can break and they can interfere with one another. They can also be diffracted around obstacles. Wind waves can be deep water waves if the water is more than half their wavelength deep. And the waves of very long wavelengths are always in shallow water, such as tsunamis are always in shallow water, and water less than half their wavelength. And these long waves travel at very high speeds with great destructive power. All right, that will wrap up Chapter 9. Again, next we're going to take a look at what happens with tides and the very, very unique aspects of tides.